Well, hi again. We're going to have a look at some differentiation, and specifically we're going to have a look at applications of differentiation, and in particular we're going to look at tangents and normals as examples of where you can use differentiation techniques to get some information about lines on a curve. Okay, it's very exciting stuff. So let's have a little go. We've got a question here which is asking us to find the equation of the tangent of the curve y equals x cubed plus a half of x squared at the point where x equals 1. Okay? Now, this is an interesting question. We've got to work out a strategy. So what I think we should do is the following. First of all, we better find the gradient function, because in order to find the tangent at the curve, we need to know the gradient of the curve, which is the same as the gradient of the tangent. So that's why we first of all need to, step 1, find the gradient function. Step 2, we're going to substitute 1 into that function there, that gradient function, to get the gradient, the actual gradient, the numerical gradient of y when x equals 1. Okay, that'll get us the actual number of the gradient when x is 1, because that's going to be the gradient of the tangent, because they are one and the same. Okay, the gradient of the curve and the gradient of the tangent are the same at that point, x equals 1. Thirdly, we're then going to substitute x as 1 into that expression for y to get the value of y at that point. And then, once we've got all that information, we have our knockout punch, which means we're going to use the equation of a line, or e.g. the tangent line, y equals mx plus c, knowing x and y because we found them in the y in the step 3, and we've got x because they gave that to us, that was 1, and then we found m in step 2, having found the gradient function in step 1. So that's mighty fine, so let's do it. Okay, step 1, dy dx equals 3x squared plus x. Do you agree? Look at that red circled function up there and tell me you agree with me. Good. Okay, you do. Good. Okay, let's do step 2, that is sub x is 1 into that gradient function to get the gradient, the numerical value of the gradient, which is 4 when x is 1. Okay. Step 3, now we're going to sub x into the original expression for the graph to get y, and that's going to be 3 over 2. Great. Now, I think we're ready set now for the knockout punch. Snail trail away, and the knockout punch tells us that the tangent line is y equals mx plus c, where x is 1, y is 3 over 2, as found in step 3, and m is 4, as found out in step 2. Okay, so let's do it. And c is the only thing left as a pronumeral in the expression for that straight line. So it becomes an easy matter to fix it and to solve for c. There it goes, and there it goes. It's minus 5 over 2. So we've got everything we need now, and our tangent line is revealed. Y equals 4x minus 5 over 2, and it's time for Mr. Box to come and finish it off for us. Thank you, Mr. Box. And there it is. That's our answer. Well, now that was a very, very doable question, wasn't it? Okay, now you can do that. You can do that. Oh, there's the calculator. Now this is a nifty little command. This is the tangent line command, okay? So that comes from the calculus menu. Tangent line, then you put the function name or the equation name in x, and then you put comma, then you put x, meaning with respect to x, and then you put a comma, and then you put the value of x that you want it at. There it is, when x is 1. Okay, so it's equation, comma, x, comma, value of x. Okay, and then you just hit enter and you get the equation on the right hand side. So what do you think, Smiley? technology is cool. I agree with you. I do agree with you. It's very cool. So, let's proceed, shall we? What have we got to do now? Find the equation of the normal to the curve. Oh, not the tangent, but the normal to the curve with equation y equals x cubed minus 2x squared at the point x is 1 and y is minus 1. Well, that's basically the same procedure, except that we don't want the equation of the tangent line, which is the same as the equation of the actual function. I mean the gradient of the actual function. We don't want the gradient of the tangent line, which is the same as the gradient of the function. We want the gradient of the normal, which is a perpendicular gradient to that of the tangent and the curve at the point when x is 1. So the procedure is pretty well similar, but let's just show you. Here's the strategy. 1. Find the gradient function as before, okay? That's dy dx, yes. Now, 2. Substitute x is 1 into that gradient function to find the value of the gradient when x is 1. That was also the same as before. However, this time we're going to use the rule for perpendicular lines, which is m1 times m2 is negative 1, to find the gradient of the normal when x is 1. Now, m1 is the symbol for the gradient of line 1, m2 is the symbol for the gradient of line 2 being a perpendicular line to line 1, okay? That you use that little equation to work out the gradient of the normal, okay? And number 4, we're going to do exactly the same thing as we did in the previous example, okay? Same thing. So it's extremely similar, except for the little m1 times m2 equals minus 1 thrown in. All right, so let's do it. Oh, we've got y equals x cubed minus 2x squared, which is, yes, that's right. And we're going to do the dy dx now. Okay, 3x squared minus 4x, very good. And then we're going to substitute that value of x is 1 into the gradient function, which we got above, to find the actual gradient when x is 1. And that's minus 1. Now, here comes the old m1 times m2 equals negative 1 trick. That tells you that if you apply that equation with m1 is minus 1, m2 has to come out as plus 1, which is a perpendicular line. Good. Now we've got everything we need for the knockout punch, okay? Here it comes. The line required for the normal line is y equals mx plus c, where we know x was 1, y is minus 1, and m is plus 1. So c is the only one we haven't got, and he is going to be found out, okay? Reveal yourself to us, Mr. C. What are you? You are Mr. Negative 2. Very good. So, no, not snail trail. The answer is y equals x minus 2. There it is. That's the normal line to the curve at the point 1 and minus 1. Okay, Mr. Box, thank you. And I think that's it. Now we better go and do the calculator version now. Oh, this is the other very nifty command. This is normal line command, which is also from the calculus menu. So you just put in normal line, the function in terms of x, meaning with respect to x, and then you just put the value of x, which in this case was 1, and you'll get that expression on the right hand side, which was x minus 2. There it is. It's just marvellous, isn't it? So there you go. So we've done that one too, alright? Alright, we're nearly there now. We're just going to keep going now with the last couple of examples. We have to find the equation of the tangent of A, f of x equals x to the third, where x is 0, and B, f of x equals x to the 2/3. If you're astute, you'll realise that that's really the square of the first function there in part A. X to the 2/3 is x to the 1/3 all squared, both where x equals 0. Well, I'm smelling a bit of a rat here. That's because I've done a few of these, but the rat will become evident. Watch this. Part A. Now, let's do the gradient function. Right, That's 1/3 of x to the minus 2/3, isn't it? Right, so what's that really in English? That's 1/3 times x to the 2/3. But hang on, the alarm bells just went off. Can you hear those alarm bells? They're ringing in my ear very, very loudly. Because if you read the question, we're supposed to be finding the gradient where x is 0. Now can you hear those alarm bells? They're extremely loud. Yes, that's right. That's right. So we can't divide by 0. So we've got a very big problem. F dashed of x is not defined. So we can't even do any more. That means that this question is a booby trap. Okay? That's right. That's the graph. Look, it's vertical at x equals 0. And a vertical gradient is a non-defined gradient. It has all rise and no run, and you're dividing by 0. So can't do that. So that one does not work. Therefore, the equation of the tangent is not defined. Okay, is not defined at that point. All right, let's do B, and I think we're going to find exactly the same rat emerging here. That's my prediction. Okay, f dashed of x equals that thing, doesn't it? Yeah, look, same thing. 2/3 x to the third, and of course, if you're dividing by x to the third, when x is 0, you'd be dividing by 0, so we've got another similar rat in our ship. There it is. Our mathematical ship is going to sink if we try to do any more with that. Oh, good heavens above, look at the graph. Yes, it's just squaring the graph which we got in the previous part A. And you remember the graph from the previous part A was dipping under the x-axis on the left-hand side of the y-axis, in other words, the lower left quadrant. And if you square it, because f of x is x to the 2/3, or in other words, x to the third all squared, anything negative becomes positive if you square it. So it just zips up to the positive area of y, and you get that funny looking shape there, and it's got two problems. First of all, the graph is vertical on both sides. That's a mirror image. On the y-axis is actually like the mirror. It's a mirror image left and right of the y-axis. It's vertical either side, so how can you define a gradient when it's a vertical line? Can't do it. And secondly, there's a cusp there, or a kink. It's not smooth where x equals 0. So for that reason, you can't define it either when x equals 0. So that's another booby trap. Okay, get the deal? Pretty easy, eh? And I think, yes, f dash x is not defined. So I think that's all we've got. Do you see how to do them? They're pretty simple. If you're not sure, just have another look at the way I went about it. Try to get a strategy. Try to implement that strategy, and then reread the question before you leave it to make sure you've actually answered it in exactly the way that they have asked you to do so, okay? All right then, well, thanks so much again, and we'll catch you next time.